I'll begin. So let's see. Today is Wednesday. Next Wednesday, the last day of class, we're going to do course evaluations. I'm also going to give you an opportunity to give me more specific feedback that is more useful to me via a Qualtrics survey. I will send out an email with an invitation to do that, and if you give me your responses of any kind, they'll be anonymous, but you'll get 1 point in exchange for doing it for extra credit. I can set it up so that it tells me which email addresses have done the survey, but the responses are not linked to the emails, so that way you can give me more feedback than just, I liked this class on a scale of 1 to 5, which tells me nothing about what to do better or worse. So be ready for that on next Wednesday. Coincidentally, we have one more quiz to do, which will likely happen on that day as well, so that I can ensure participation in the evaluation process. So speaking of the evaluation process, I have to give you guys a big round of applause for being really good at turning in your assignments on time. Honestly, you guys have been like my best class in like 12 years. There's only been 1 or 2 straggling assignments. That's usually not the case, so yay. What that means is that I can go over them because we're not waiting on a bunch of people to finish them. So I thought it might be helpful to go over assignment 6. Would that be useful? Like degrees of freedom, maybe, Erin? You're asking me about that? She's like, yeah, maybe. So here is assignment 6. This is the piecewise model, the longest assignment I think you'll have this semester. So the computational questions for the most part went pretty well. Significant person dependency. That's the idea of interclass correlation. So you have a significance test for whether it's greater than 0, and you have an effect size for it, which is the interclass correlation. Let's see, we had a couple people mess up this little part right here. So the interclass correlation in these simulated data was meant to be low. So for everyone, I believe it was less than 0.5. So an interclass correlation smaller than 0.5 means more of the variation is within than between. More of the variation is level 1 than level 2. More of the variation is over time rather than on average. So I was looking at the combination here of you getting the within parsons right, the over time versus on average. A random intercept between person variance is in the mean, so that's the average part. So within and over time should go together. With nothing else in the model, the expected stress is on average over time. The F test for whether or not there's any change over time at this point, this is your omnibus main effect of time. So otherwise known as the saturated means model. There were 13 occasions. That means it's a 12-degree freedom test as to whether there's any kind of change whatsoever. All of you should have had a significant result for that. And that gives you then impetus to go forward and try to model the change with some kind of functional form. Okay. So then I had you set up some slopes. So the first part then was just making sure that your slopes were set up correctly. We went over that in class, and so I think that went relatively well. Then we added linear slopes for each part, from 1 to 7, 7 to 8, and then 8 to 13. I had you then test whether or not that was good enough. So we have linear change here, and then we have a test statistic for the difference in fit relative to the saturated means random intercept model. So the two models to be compared here, we have fixed linear random intercept versus saturated means random intercept. So they differ in their model for the means and their fixed effects. Because I had you use maximum likelihood, you can do that with a -2 log likelihood comparison. Had you been in REML, you could have done that with a contrast statement. That's the trick where you add in session as a main effect, and you can get all the missing degrees of freedom. And then you would have, here's your -2 log likelihood difference and a p-value that goes with it. Now, degrees of freedom. How do you figure that out? This is a tricky one, right? So saturated means model has as many parameters as you have occasions, right? So in this story, that is 13. If I have linear slopes for each of my 3 phases, that means I have a fixed intercept and 3 more slopes. 1, 2, 3, 4. 4 minus 13 is 9. We then added quadratic slopes for the first and third phases and compared that back to the saturated means model, and that should have been either non-significant or very close to it for most of you, in which case that's a 7 degrees of freedom difference, because now you're comparing 6 versus 13. Yeah?
But so for the fixed linear versus saturated, we're taking 4 away?
You're saying, is 4 good enough to be 13? So relative to the saturated means model, the model with only 4 parameters has to fit worse. The question is it significantly worse? So that's a worse, not worse question in the way that it was worded down below. So let me find the text that goes with that here. So relative to saturated means, this fixed linear model fit significantly worse. Degrees of freedom equals 9. The idea is that had the linear model been sufficient, there would be no difference between letting all the means be whatever they wanted and what the model says the means would be as given by linear trajectories. That's the idea. It's a test of absolute fit of the means over time. We then added the quadratic slopes, and the question is here, to test whether the assumption of constant change held, that's code words for linear change, quadratic slopes were added to the before and after test phases, resulting in, and this one's a better, because you're going from linear to quadratic. You had 4 things, now you have 6. So whenever you add parameters, it's better or not better. In this case, for this student, it fits significantly better. And so then the question is, okay, well, we're moving in the right direction. We knew that a linear set of trajectories was not good enough, but quadratic made it better. So is quadratic good enough? So that's 13 versus 6 for my new linear and plus quadratic model, and that's a degrees of freedom of 7. So in this case, yes, the quadratic model did accurately reproduce the saturated means. Does that make sense? Or is there anything you'd like to ask about that doesn't yet make sense? Lucas, you want to, I can see it.
I was wondering about number 45 and 49 computational questions. The estimate of the linear rate of change. I'm not for the life of me figuring that one out. I thought it was the first derivative, but
It is the first derivative, but at a particular occasion it changes, right? So it's the instantaneous linear slope at a particular occasion. The one that's given to you in the model is not at occasion 1, it's occasion 7, because that's where the intercept is. Normally it's occasion 1, but I decided to trick you. Yeah, so in this case, this one came first. That was my way of trying not to trick you, right? Remember, like, this is the one that's found on the output. Now what happens to it according to the model? It becomes different by the quadratic, twice the quadratic per occasion. So then that's an estimate statement. Let me see what the direction is in this case. Let me see if I can figure that out from the numbers here. Yeah, so in this case, this is what the fixed linear trend would be for slope 1. This is the fixed quadratic trend for slope 1. So that combination then, that is a, if you're going forward in time, it's going to be more positive. If you're going backwards in time, which is what it would be when you subtract from 7 to 1, then it would be a less positive. So this is my way of trying to help you figure out the pattern by asking you sort of, okay, what is it at the beginning, what is it at the end, so you can see The idea is that as the test gets closer, the increase in stress increases. People start freaking out. That's the story. So the linear rate of change at occasion 8 is this one. The linear rate of change at occasion 13, then you'd have to do an estimate statement to get out to that point. And the quadratic rate of change here, this one is a positive one, so it looks like this is a more positive as well. Okay. Yeah, so the section 3 results question, those ones were fairly straightforward. You were adding random slopes in one at a time, just for the linears. I could have had you run the quadratics, but I was worried about the models not converging in any kind of a speedy fashion, so I decided not to do that for you. But we start with a random intercept, right? We add in a random linear slope for the first slope. That's degrees of freedom 2. We add in a third random effect. That's degrees of freedom 3. We add in a fourth random effect. That's degrees of freedom 4. And had I asked you to do a fifth one, what would the degrees of freedom be? 5. Yes. Because each time you are adding the variance of the new random effect plus its covariance with all the random effects that are already there. And each random effect then is referring to some kind of individual variability in linear change. You just have to pick which idea goes with which slope. Before the test, right after the test, or yeah, I call this acute change, and then as they're waiting for the results afterwards. Yes, I think that was it. So you should have the green answers that are correct and the red ones that you gave. If you have any questions about why you got something wrong, I'd be happy to help clarify. Okay. Any other questions? Okay, well then homework 7 is due on Friday. We went over that one last time. And I just put up homework 8 today. So those of you who are looking to finish your semester quickly, go for it. You should be able to get through quite a bit of it after lecture today and probably all of it after Monday. That's the idea. So that one is up. Yeah, and so your grades should be current, I think, for the most of you. Any other questions? Okay, you ready to do time invariant predictors? Ready to finally get to some karate? Instead of, you know, cleaning the deck and whatnot? Wax on, wax off, paint the fence. So first, some bad news with respect to what happens to missing predictors, and then how do we put these time invariant predictors in the model? So, missingness. Missingness is often a problem in longitudinal data, and there's lots of reasons why it can happen. You can have people just not cooperate at a particular occasion. You can have them not come back. A special form of missingness is what I would call unbalanced data, where not everybody has the same measurement occasions. You can think of that as a type of missing data, although I tend to use unbalanced instead. Planned missing data, that's something that you don't want to have to do unless you absolutely have to. Like if you're trying to collect 1,000 survey items from people, but you only have enough money to pay them for a half hour of their time, that's not going to work. So planned missingness is a way to very carefully give people only parts of the outcomes and try to piece back together what the overall response pattern would be using full information maximum likelihood. The other thing that people don't often think about is that the same selection bias that people say with respect to attrition is also present at the beginning. You always only get the people who are willing to participate. So think about that in terms of generalizing to some kind of population from your sample. Any kind of missing data handling or procedure or analysis, the goal is never to figure out what the missing data would have been. The goal is always to figure out what the parameters would have been had you not had missing data. And so even when you're doing something like imputation, which is literally filling in the values, The values aren't the point. The values are the parameters that come back, your slopes, your random effects variances, and that kind of thing. Every kind of method that you're using to address missing data requires some kind of assumption, some of which are not testable. So things not to do and what to do. Never, ever, 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 ever do any kind of imputation that involves one round. So in SPSS, for instance, there are options for doing single mean replacements for missing data, or what's called a regression imputation. You cannot fill in missing values without considering some kind of error in the process. It's totally cheating and you can never do it. Preferably not is leastwise deletion. Whenever possible, you want to try to use whatever data you have and not get rid of whole people. Now that being said, sometimes you end up getting rid of whole people because of the model that you're running. So what to do? And this topic, by the way, could be an entire semester's class. I think we used to offer a class on missing data. I don't know if it's coming back, but it is in and of itself a topic. So this is just a brief overview. If you're looking for a very readable introduction, I would recommend Craig Ender's book. I gave you chapters 3 through 5 out of that. It's a applied missing data, I think is what it's called. Very readable book. He has M+ examples online that go with it, so I really like that book. It's a lot easier to read than some of the more statsy versions of missing data treatment. So the term full information. Full information just means that you're using all of the original data to estimate the model rather than a summary thereof. Limited information versus full information is really only a distinction that is made in categorical data analysis nowadays. So if you're doing a model where you have binary data or count data or categorical data or something like that, then limited versus full is something you have to think about. But if you're doing a model in which all residuals are supposed to be normal, full information maximum likelihood is what you get by default in all the packages. Just as a FYI, REML is also full information. But for whatever reason, there is no such thing as FREML, even though there is a FIML. But they're both full information. So there's nothing bad about REML relative to ML with respect to missing data. M+ and mixed, all the mixed packages, Stata, SPSS, SAS, all of that, they all use full information maximum likelihood whenever you are dealing with normal outcomes. Whether or not to do imputation versus full information maximum likelihood, if you're talking about missing outcomes, it really is 6 of one, half dozen of the other. Given the same missingness model, meaning that you have the same variables in that are supposed to be related to either the outcome or the missingness or both, asymptotically equivalent results will be found when using multiple imputation versus full information maximum likelihood. The latter is way easier to do in practice. The downside for all of this, though, is that both of those make an assumption called missing at random, which is not empirically testable. So these are phrases that you've probably heard before, and if not, I'll go over them quickly. Completely at random is a way to characterize missing data that is exactly what it sounds. Like if you're giving out a questionnaire and for whatever reason the copy machine ate one of your pages and that's why people didn't get it, that's completely at random. It has nothing to do with what they would have said. Missing at random means conditionally random. It means after you take into account what you do know about the person, it's then random. So among similar people, there's no relationship between what they would have said and the probability of it being missing. So variables that count in terms of helping that are predictors and other outcomes. So for instance, if I have somebody who's not doing well in my longitudinal study, they show a negative trajectory. If they don't come on the 4th occasion here, the model can probably do a decent job capturing the fact that it still would have been a negative trajectory. That's missing at random, this idea that it's not completely random, but once you condition on what you do know about them, you can probably make a pretty good inference. If all of a sudden they recovered and you never found them again, they started coming back up, my marker hasn't recovered. If they start coming back up, but you haven't measured that, That's an example of the last one, not at random, which is exactly what it sounds like. Then you are some shade of wrong no matter what you do. As I said, the bad news, these are not testable. Completely at random is the only one that's testable, because if there's anything in your data set that is related to the probability of a missing value, you know it can't possibly be completely at random. But you can't actually test missing at random because you lack the information with which to do so. So this is one of my reviewers tend to love to complain about this because they know there's no answer. Well, I don't think that the random and the attrition are bad. And all you can say to that is, yes, it's not testable, but we have included XYZ covariates in the model to try and help justify the missing at random assumption. That's all you can say. So if you happen to know why it is somebody didn't come back, if they changed schools, or if they told you they don't like your study, any information that you have about why you have missingness, put that in the model as a predictor. Even if you don't care about it as a predictor, it will help with the missing data assumptions. So that's for missing outcomes. Now the bad news. What about missing predictors? We talked about this at the beginning of the semester, but chances are if you have an outcome, you know what time it was. So we haven't really had to deal with this, but now it's going to bite us. So MLM handles missing data, yes or no? Not really. It operates the same way as any other procedure that assumes listwise deletion. It uses listwise deletion, it just doesn't delete whole people. Every row has to be complete. A row in your data set is an occasion within a person. So time is likely measured if you have the outcome at that occasion, but your predictors may not be. So your sample size may change across models depending on which predictors you've included and their patterns of missingness. You cannot do any kind of model comparison involving -2 log likelihood, AIC, or BIC if your sample size changes. -2 log likelihood is literally the sum of the log likelihoods for each person. It will change if you have different people contributing to the sum, regardless of whether the predictors help your model. So one option then to prevent this problem is to think about which predictors you're eventually going to all want to have in your model and pre-select your sample to be complete. That's one way to solve the problem. That's a really bad idea if you happen to have a lot of missing data though. So then what do you do about it? So just to illustrate how bad the problem can be, here's an example of a multivariate data set on the top here. This is what you would enter into like a repeated measures ANOVA. And the same data set stacked so that one row is an occasion within a person rather than a person. So I have a time variable here, a dependent variable, a person level predictor, and a time varying predictor here. So if I only have an unconditional time model, just time predicting my outcome, which rows go in? The answers are in front of you, so you could participate that way. Which ones? All of them except 7. 7 doesn't have an outcome, so 7's out. How about if we have time and the time varying predictor? 1, 2, 3, not 4, 5, not 6, not 7, 8. How about the person predictor? Yeah, rut row. This is where MLM will do listwise deletion because every single row is incomplete for that person if you're missing a person level predictor. And if you have time varying predictors and person predictors, then you get only 1 to 3. So throwing out rows is never the best idea. It may be what you're stuck with. The alternatives. So this is a question that I posed to Craig Enders once in terms of what you're actually assuming about missing predictors. And he said that unquestionably, whenever you have missing person level predictors, time invariant predictors, omitting them is assuming that they're missing completely at random because the person is gone from the analysis, and so there's no way to know what you're missing because they're gone. If you have a time varying predictor that is missing, he was like, it's somewhere between missing at random and completely at random. Even though it's not in the likelihood, you do have some values of the time varying predictor for the person, so it's kind of like you can condition on what you do have. So it's somewhere in the middle of those things. And so there are other ways of addressing this problem, but they are not without their own problems. So this is the point at which some other reviewer, if you end up throwing cases out because of missing predictors, will say, well, what about structural equation modeling? Structural equation modeling handles missing data, right? Yes and no. Programs like M+, and as is the default, and I think a lot of other SEM packages, they require missingness. Let me back up here. They require predictors or outcomes that have missing data to be treated as outcomes in order for those cases to not get deleted. What that means is that rather than just saying, I'm trying to predict Y, and how Y is predicted is inconsequential, I'm now trying to predict what X is and Y is. And so the mean, the variance, and the covariance of all your predictors become part of the likelihood. They become things that it's trying to find iteratively. So even though you're thinking of it as a predictor, the algorithm is thinking of it as an outcome, which means the predictor then has the same distributional assumptions that the outcome has. Normal in most cases. So if you have something like, let's see, I'm coming up with something that's categorical that's not gender. SES, and you've categorized it into like 4 levels or something. If you don't have an SES for somebody, throwing it in the likelihood means you're assuming that it's normally distributed. A 4-category variable is unlikely to be normally distributed. In M+, you can tell it that your outcomes have different distributions, but it won't let you do that unless it truly is an outcome in the sense of being predicted. So you may actually have to take your predictor and have something else predict it just to deal with the missingness. And it adds another dimension to the estimation in terms of integration if you're doing that with categorical data. So point being, if you allow missingness on predictors by bringing it into the likelihood, you're making distributional assumptions about the predictor. Just be aware of that. The same is true if you use multiple imputation to address missing predictors. All imputation models have some kind of distribution that they're working with. It's normal if you don't get it to choice. Like if you use proc-mi, it's normal. The other piece of this, if you're using multiple imputation, is that the imputation model, the things that you're using to try and predict what the missing values would have been, that model has to have everything in it that you would eventually want to be part of your analysis model. So that includes not only main effects of predictors, but also interaction terms. If the predictors then, even if they have a normal distribution, an interaction variable can't possibly be normal. It will be skewed. The downside for this with respect to longitudinal data is that the missingness model then in theory should include all possible random slopes that you would ever want to look at. But every random slope adds another dimension to the log likelihood mountain that the thing is trying to climb. And it may be impossible to get them all in. So what to do with missing predictors in multi-level or longitudinal models is an active area of research. I would refer you to Craig's work, Craig Enders, and other people who are working on the problem as to what to do. There are a series of options, but there is no one right answer. So because of that, and because we're working in mixed for the time being, I'm going to take the approach where I delete any people from the sample who are missing any of the time invariant predictors. It's not great, but it's what I'm going to do for now. If you stick around next semester and we get into running the same types of models with an M+, I can show you how to bring the predictors into the likelihood, treat them as outcomes, and then we'll do multivariate versions of these same models that help solve the missing data issues. Okay? So from now on though, if someone asks you, well, doesn't MLM handle missing data? You're going to tell them what? Kinda. It doesn't fix it. It lets you keep whatever rows are complete. That's what it does. But they have to be complete with respect to the predictors and the outcomes. That's the deal. All right, so now the good news. This, what we're going to do here, is going to be way easier than what we've done previously. Do you know why? Because we're talking about level 2 predictors. Level 2 predictors can only have fixed effects. Level 2 predictors cannot have random effects because there's no higher level of sampling for their effects to be random over. So that means that from this point out here, the next week and a half or so, this is going to look a lot like what you learned how to do in any kind of regression type class. We're adding predictors into a model. We're going to look at main effects, we're going to look at interactions, and we're going to see what's significant and how much variance they account for. The same story as usual. Now the only catch is that we're trying to predict multiple outcomes at the same time. Each pile of variance has the potential to be predicted, and we can calculate how well the model did with respect to each pile of variance. So that's where the complexity comes in. But conceptually, this is no different than any other linear model thing that you already know how to do. So synonyms here: time invariant predictors, level 2 predictors in this context, person things, things that they walked in the door with, things that you only measured once, either because you didn't need to measure it more than once, or just because you could only measure it once, but measured once is the key. We're going to center time invariant predictors. We've talked a lot about this. Continuous predictors, someplace in the middle is good, doesn't have to be the grand mean. Categorical predictors, I tend not to do effects coding except for very rare circumstances. I do dummy coding, somebody's got to be the 0. If you let SAS code your categorical predictors via the class statement, it makes somebody the 0, and that is the highest group alphabetically or numerically. So what can time invariant predictors do in a longitudinal model? It's pretty straightforward. If you're in a within-person change model, they adjust your growth curve. That's it. So for instance, if I have a control versus treatment here by the different lines, this is what a main effect of group would look like. A main effect of a time invariant predictor adjusts the intercept. It makes one group higher all the time than the other. If I added an interaction of group with time, I could get a prediction that looks like this: different slopes for different groups. Now I have main effect of X question mark here, because whether or not a main effective group would be significant given this pattern depends. What does it depend on? Time. What about time? Where is the main effective group going to be once we include group by time? You know this. It's not different. If I have the main effective group, the main effective time, and group by time, the main effective group becomes the simple main effect when time is 0. So whether or not that happens to be significant depends on where time 0 is. In this picture, if I centered time where 0 is the first occasion, I may not have a significant main effective group. If I centered time such that 0 was at the end, it might be significant by then. Regardless of where time 0 happens to be, you can get the expected group difference at any time via estimate statements. And you could have something that looks like this, where both is true. One group is always higher. The extent to which that occurs depends on time. Or you can think of it as one group has a higher intercept and a steeper slope. If time is irrelevant, if you're in a fluctuation model, then you kind of just have intercept differences, and that's about it. Austin. Yes, yeah, we are time invariant for the rest of the year. Time varying is like a 2-month topic.
Conceptually speaking, aren't you
it's gonna be the same value like over time. And if you add this time variable of interaction, then you're like increasing that, although it stays the same, I guess.
You mean the variable that you're making that's the multiplicative term?
Yeah, that's the same within like adding this time, which like can change automatically, I guess, in a way. So isn't that kind of inflating? Like you're almost like creating it to change over time because you're like with that interaction. Does that make sense?
It changes over, group in that case would change over time, but it would change over time in the same way. So if I had group by time, let's say in this picture, and I'm let's say if it's time 1 times group, then you would have like a 1 unit difference. And then if you multiplied it by time, like whatever group was, it would still be the same distance. I'm not saying this very well. Another way to think about a group by time interaction is whether the effective group changes over time. You can talk about it as whether the effective time varies by group or whether group matters more at certain occasions. So that the group by time gives you a chance to see whether or not which group you're in matters more if time is higher than if it does if it's lower. It's not time varying though, because the way that people in the group change is all the same across time. Like everybody would have the same group by time term if they're in one group, and they'd have a different value if they were in the other. Does that help?
I'm just thinking like of a coding scheme, like
Mm-hmm.
say, let's say with a high, like low, medium, and high SES. So if you had low was like you put it as 1, medium 2, high 3,
Mm-hmm.
for example, and then you do that interaction with the time variable. And like, so at time 1, it's gonna be like you do the interaction term that's gonna be 1 because it's, for like group 1 is 1, but then for group 2 it's gonna be 2 times the 1, so that's 2, and so 3. So you're automatically creating these differences, I guess, in how much the coefficient is multiplied by or the estimate is multiplied by that.
Yes, but it's the same for everybody within a group. And in that example, you would actually need 2 different effects of group to distinguish the 1s from the 2s and the 2s from the 3s. Because otherwise it wouldn't. Well, if you thought of it as a continuous variable, then you'd only need 1. But if it was groups, then assuming that 1 versus 2 is the same as 2 versus 3 probably doesn't make a lot of sense. So yeah, it's not time varying because it doesn't vary. Like once you know what group it is and what time it is, that's it. There's no other variation left. Like that's perfectly identified in that case. A time varying predictor would be like if group varied within persons. So like an N of 1 design where you're trying to make like some kid get off the couch or something. And some days you send them a text message that says, hey, get off the couch, and some days you don't. Then like that's an intervention design where it's within persons. And so that would be a time varying effective group, because then you would compare days where you got the message to days you didn't. So that would be different in that case. So yeah, time invariant, it explains level 2 variances, intercepts, and slopes. If you don't have slopes, then it just does intercepts. Another thing that it can do, which is something we'll get to next semester because it's a little tricky to implement, is time invariant predictors can predict heterogeneity of variance. So if you think about what these models assume, it's constant variance across people in the variance terms. So with respect to the random effects, it assumes that there's no like hidden piles of people that are more or less variable from each other. And it assumes the same about the residual variance. So one of the questions, though, that you can ask, especially with level 2 predictors that are grouping variables, is whether or not variability differs between groups as well as the mean. So for instance, if I had, is this the height one? Yeah. So if I had something like boys and girls and changes in height over time, it might be the case that boys are taller and grow more quickly. That's a gender effect on the mean. But it might also be the case that there are more differences between boys than there are differences between girls, such that boys need a different random intercept variance than do girls, and they might need a different random slope variance too. The way that you would implement that is to give each group its own G matrix in SAS And you can do that easily by adding group equals after the slash. Just like any other addition to the variance side of the model, that's a -2 log likelihood test waiting to happen. The only downside is that you can't test very easily if it's just the intercept that needs to be different or just the slope. You're testing the whole G matrix as a set. So if this was a random intercept and linear slope model, that would be degrees of freedom of 3 for all the terms in the G matrix to be compared. On the within side, on the residual side, if we think about something like variability in positive and negative mood, these models assume constant residual variance. These models assume that the within person variation characterized by residual variance is the same across people. In the context of mood, that means that these models by default assume that everybody is equally moody. Some people might be happier or sadder on average, but they're assuming that the fluctuation is the same. So you can add time invariant or time varying predictors as predictors of the amount of residual variance as well. Who was I talking to about this? Is it Amy? No, I swear I was. You had something that was going to do this. It was some project you were talking to me about. Yeah, so you're looking at glucose regulation, right? So fluctuation over time, either throughout the day or across days. And the extent to which some people are more regulated, that's a difference in residual variance as a function of a time invariant predictor. Those are called location scale models, and they are tricky to estimate. You can do them to SAS in some extent. NL mixed is a lot more flexible than SAS proc mixed. M+ version 8 just added this as a new feature. So next semester I will show you more about how to do that. But just think about that as another type of hypothesis test that you can engage in, predicting differences in variability as well as differences in mean. The good news then, we cannot have random slopes for level 2 predictors. So to illustrate why that is, let's think about what a random slope for time means. If I have my pink person and my blue person, time is a time varying predictor on the x-axis. Each person in this picture has 4 distinct values of time through which I can fit their own slope. But if I have something like biological sex, the sex they're born with, or any other level 2 predictor that I've measured once, every time I ask them, they'll have the same value. It's a dot, 1 dot. You cannot make a line out of a dot. Each person could not have their own effective sex because sex does not vary within persons, so we can't see what the effect of within person variation is if we don't have any. Now I could draw a line between the blue dot and the pink dot, and that would be a fixed effect. And if I had a level 3, like schools for instance, I could see whether the difference between pink and blue varies over schools. But without a level 3, my level 2 predictors can only have fixed effects. So that makes it relatively more straightforward than otherwise. Okay. How are we doing? We're doing? Everyone showed up all like smiley and chatting today, and now you're like... The only person who's allowed to look all slumpy is Katie right now, because she's like, I slept a half hour last night and I'm here. Yeah, I remember. I remember that oh so well. But yes. So let me show you what it looks like. As an example, what would the model look like if I had something like years of education? Let's say that I am measuring adults. So most adults do not change in education unless they're specifically going back to school. So let's just call that a level 2 predictor for sake of illustration. And let's see what it would look like in a model that has 2 kinds of random effects of time. This one is a quadratic. We could do it with a piecewise or any other type of growth model. That means that if I have a random intercept, a random linear slope for time, and a random quadratic slope for time, there are 3 potential roles for a time invariant predictor like education to fulfill. A main effect, think of that as an interaction with the intercept. It makes the expected value at time 0 go up or down. The effect of education on the linear time slope makes the linear time slope increase or decrease, conditional on time 0 in this model. And education can also make the quadratic time slope increase or decrease. So it would look like this. So here's my level 1 model. Now the subscripts are going to start making more sense, I hope, because you'll be able to see the pattern. But just to review here, y is my outcome at each time t for each individual I. Each person gets their own intercept, beta 0 I, which is a placeholder. Their placeholder for the linear effective time, and their placeholder for the the quadratic effective time. Note that every variable that is in the level 1 model gets a ti subscript. I've got y per time, e per time, and time per time. Because I have 3 beta placeholders, I have 3 level 2 equations, 1 for each. In these level 2 equations, the first subscript goes with which beta it's predicting. So beta 0 here, I've got a 0 here, a 0 here, and a 0 here. For beta 1, I've got a 1, 1, 1. For beta 2, I've got a 2, 2, 2. Within the fixed effects then, the red terms, the second subscript indicates the order of the predictor within the level 2 equation. So each of these starts with just a fixed effect. If I have no predictors, we call that an unconditional growth model. So the first term here starts with the 0 in the second subscript. Then I have the first predictor of beta 0. This is the first predictor of beta 1. And this is the first predictor of beta 2. So if I added something else in here, for instance, if I wanted to add another predictor of beta 0, what would its subscript be? 0, 2. And another one? 0, 3. How about if I wanted to do one here? If I wanted a second predictor of beta 1? 1, 2. And the second predictor of beta 2? 2, 2. That's what they mean. Okay. So with respect to conditionality here, the you are here sign, this is my fixed intercept, right? Because of time as a level 1 predictor, we know that this is going to be for time 0. Now it is also going to be for ed equals 0 because we've added education. In this example, education is centered so that 12 years is my 0. So this gamma 0, 0 right here, this y-looking thing, 0, 0, that's my expected outcome at time 0 for a high school graduate. Okay, from there, for every unit increase in education, gamma 01 gives me the change in the intercept. U0 then. Previously we defined fixed as everybody gets the same and random as everybody gets their own, right? Remember that? Remember that? Do we need to stand up? I have like a 12-pack of dew in my office. I'd be willing to share if that meant some more liveliness. You're like, hmm? Because you can't get Diet Mountain Dew in this entire building. Did you know that? It's true. They put in like iced tea instead where it should go. That's BS. Do I look like my mom? No. Sorry, I think of iced tea as like an old lady thing. It's just, I would never pick iced tea out of a vending machine. But I digress. Fixed, everybody gets the same. Random, everybody gets their own, right? Still true. Gamma 01 does not have an I because that is the effect of education on the intercept. It's fixed. Everybody gets that same increase to their intercept based on their education level. So that means all high school graduates have the same intercept. All college graduates have the same intercept. U0 then still is the difference between your intercept and the fixed one. It's just now it's the fixed one predicted by your education level. So it's not how far off you are from average, it's how far off you are from the conditional average given by the predictors. Yes. So U0 used to be how far off my intercept was from the average intercept. Now U0 is how far off is my intercept from the conditional average given by my predictor. So you can think of U0 as representing deviation among people with the same education level. I've already adjusted my intercept for the difference between high school and college and whatnot. But that doesn't explain all the reasons why the intercept differs. U0 is the deviation from there, from the conditional intercept given by my predictors. So U0 is here to convey the idea that the model has a random intercept variance. It allows individual differences for some unknown reason in the intercept. And previously we would have tested to see if they were significant, and we can describe how big they are. Well, if education matters, if intercepts are different depending on your education, what should happen to the U0 variance? Your choices are goes up, goes down, or stays the same. If education matters, what should happen to my U0 variance relative to a model that doesn't have it? It goes down. U0 variance left over is what we have now. Random intercept differences that remain after controlling for education. For this reason, some textbooks call these random effects level 2 residuals because they're left over after predictors. I'm not going to do that to you. Residual is level 1, damn it. These are random effects left over. Deal? Terminology is important. I can't change the terminology until we at least understand one set of it. Mm-hmm. Yeah, so you're talking about significance and effect size. So yeah, gamma 01 is a fixed effect. It has a null hypothesis of 0. It could be positive or negative, so we can stare at the p-value that shows up on the output, Wald test. That's my significance test. But if you want to know, like, okay, it's significant, but like how big is it? How much does it matter? One way to characterize that is, well, how much of the intercept variance went down? Did it explain 1% of the reasons why people needed their own intercept, or did it explain like 50%? That's the effect size that goes with the significance test here.
Can we just pseudo R-square?
That's a pseudo R-square. That's what it is. Whenever you're talking about variance explained of a particular kind, a particular variance component or a particular pile, that's pseudo R-square. And we get to do the same thing for the random slopes. So beta 1i is how each person gets their linear time slope. It starts off with this one right here. So this is my fixed linear time slope. This is the instantaneous linear rate of change when time is 0. And because education is now predicting it, it's also specific to a high school graduate. Gamma 1 is the effect of education on the linear time slope. That's an interaction term. It doesn't look like it because it's just hanging out sitting there by itself. But if you do the substitution, if you fill in this linear combination up here where beta 1 is, and you multiply it out, you end up with gamma 1 times time plus gamma 1 times ed times time plus u1 times time. And that is done for you on the next slide. So on slide 16 here, the top has this written in a multi-level notation. The bottom shows what it would look like in composite notation, eliminating the beta placeholders. These are two different ways of expressing the same thing. The composite equation, I think, shows more readily how gamma 1 right here is actually ed by time. More generally, if you're looking at an equation and you see a fixed effect that has subscripts where both of them are a number of some kind, that has to be an interaction term. It is known as a cross-level interaction because time is level 1 and ed is level 2. So each person gets a unique linear slope based on their education level. From there, U1 is how far off their own linear slope is from the one that's predicted based on education. So if education predicts linear change over time, then my U1 random linear slope variance should go down. Last one, beta 2. This is how each person gets their own quadratic slope, their own rate of acceleration or deceleration. Gamma 2O is half the rate of acceleration or deceleration for education equals 12. Gamma 2.1 is how that changes per unit of education. To the extent that education predicts reasons why people need their own quadratic slope, the U2 variance should go down. So education is one predictor. Because it is a level 2 predictor, it can play up to 3 roles here. It can explain why people need their own intercepts, why they need their own linear slopes, why they need their own quadratic slopes. Now, can education explain E-variance? That's the fourth pile that we have here to contend with. By itself? No. Think about what E-variance is conceptually. It's why are you off your line today? It's misfit to the growth trajectory at each occasion. I have a PhD every day. It may not feel like it some days, but I do. So me having a PhD cannot possibly explain why I am off my line today, but I'm going to be on it tomorrow. So time invariant predictors can only capture level 2 random effect variance when they're by themselves. This down here, this is a 3-way interaction, gamma 2.1. This is ed by time by time. Boom. And now you see why I made you do lots and lots of practice with estimate statements, right? Because we're getting ready for this. This is your karate. Heather's not excited. She's like, no, I don't think so. So we've given time a quadratic effect here. Do you think education could have a quadratic effect? One second. Do you think that more education matters up to a point maybe and then it doesn't matter as much? Is that possible? What if I wanted to put education squared in? Could I do that? Could I put it right here in the intercept line? Sure. Could I put it in the linear slope line? Sure. Could I put it in the quadratic slope line? Sure. And that's a 4-way interaction. And at that point, I would have, let's count up the number of parameters here. Let's just do this picture right now. How many fixed effects are in this model? many red things? 6. 6 red things, 6 fixed effects. How many blue things? 4. How many level 2 blue things? Just 3. How many covariances among the level 2 blue things? Also 3. So if I have 6 fixed effects, 3 random effect variances, 3 random effect covariances, I'm up to 12, and a residual variance at level 1, that's 13, right? If I added in education squared as a predictor, that would be potentially up to 3 new fixed effects. That could be up to 16 parameters. How many predictors do I actually have, though? 2. 1 at each level. That's it. I can make 16 parameters out of 2 predictors. That should give you pause, because how many of you have research questions, dissertations, theses, or papers that involve only 2 predictors? Anyone? Nope. And that's why this gets complicated very, very quickly. Your question.
You said education itself. Can you explain the E?
Yes.
How about interaction with time?
Yes. That's coming. That was my SMEP talk. Yes, by itself, meaning a level 2 predictor or interactions among level 2 predictors. They cannot explain E variance. Yes. So cross-level interactions, that's what we're looking at here. Okay, questions so far? I want to skip ahead to something so I can start in the example. Slide 22. So far what we've talked about with respect to effect size is pseudo R-square predominantly. Pseudo R-square means effect size per pile. So we have time and time squared. Those account for residual variance at level 1 because time is a level 1 predictor. Education or any other time invariant predictor as a main effect captures intercept variance. Education by time would capture time slope variance. Education by time squared captures quadratic time slope variance. Another way to think about effect size, though, is what is it sort of overall, not per pile, but all put back together again. And so I want to introduce you to the idea of total R-square. I don't know that I came up with it, but I know that I put it in my book so that I could have a reference to cite in all papers from now on. That's what I know. It's very straightforward. It's the idea of taking your model, the fixed effects in your model, and asking them, okay, generate a predicted outcome. You know how to do this already, I think. I may have shown this to you. If not, it's out PM in SAS or save equals fixed pred in SPSS. And you save that column to a data set. You have the right answer also. You have your outcome. If you correlate the model predicted outcome with the real one, that's R, take that R and square it, that's R square. So it's a very intuitive way to describe just how much variance your model accounts for, putting it all back together again. So they're complementary ways of talking about effect size. You can talk about the effect of a predictor on each random effect variance, and you can talk about sort of its global effect in the terms of total R-square. Total R-square is also helpful in models that you have heterogeneous variances in, like if you allow a different variance at each occasion or for different kinds of people, then you can do this and put it all back together again. So I will show you that in our example as well. So let's look at maybe one model before we break, and then we can start looking at some of the others. Example 7 I have on deck for you. This is not in the book, by the way. This is building on the same data that we've been playing with, the practice time data, but this is not in the book. Chapter 7 in the book is different data. So this will be a third example, I think, for you to follow. So given that in the practice effects data that we ended up with, we looked at quadratic models, we looked at piecewise models, we looked at exponential models. I'm giving you an example with quadratic because that's what I'm asking you to do in homework 8. And I'm giving you an example with piecewise because they're working on. So we'll have the same set of models essentially with two different versions of growth, piecewise and then quadratic. So this part of the code here on the first page is just reiterating what we already did. We're building our time variables. So for the quadratic models, I'm creating time as session 1 here. Time 1 is session -1. I created a squared term for use in something else. And here is how I created my piecewise slopes. Change between time 1 and 2, and then from 2 to 6. This example is going to have 3 level 2 predictors, 2 of which are continuous. Age at the beginning of the study. This is a 2-week study, so this is age that is time invariant. I've centered it at 80. And abstract reasoning, a measure of crystal or fluid intelligence, excuse me. I've centered it near the scale's mean, which is 22. And then just for the sake of having a grouping variable to show you as an example, I cut up education. I would never do this on purpose. This is just for pedagogical purposes so I can show you what a group variable would look like. I cut up education into high school, college level, or graduate level. The last step then is dumping out any people who have missing information on any of these predictors. I don't want to do it, but I have to if I want to keep my models comparable. In this case, I did have complete data, but I include this step just to make the point that if you're not going to address your missing data in some other way, this is probably a good idea to do to begin with. So I'm setting a new data set, the one that has complete cases, so the n stays the same across all of my analyses. So we'll skip that part for right now. And we'll look at an unconditional model, and then we'll add age to it. So I'm starting on page 7. This is a piecewise growth model. This is my unconditional model. This is the best fitting model we ended up with on the piecewise unit from before. I am re-estimating it here to show you total R square. This part right here in the code, this is the new thing I want to emphasize. Out PM. Have you seen this before? Have I shown this to you before? Okay, good, then this is a review. It's calculating, it's going to take my data set, save it as a new data set with this name, and add columns at the end for the predicted values based on my model. At this point, the only variables that are in my model are time. So everybody has the same set of predictions based only on which time is which, but that allows me to say how much variation in response time is just due to change over time during this 2-week period, and then see how much more I can get by adding in time invariant predictors. I am also on my ODS statement here. CoveParms, that's the name of my variance components table. I am saving the estimates of my variance components so that I can then do pseudo R-square comparisons with them after adding other predictors. So they are going to be saved to someplace called CovePunc, which to me means the covariance table from the piecewise models from the unconditional model. That's my naming convention. You can call it whatever you'd like. So if I were putting these models in a results section, this model is an important thing to start with because this represents all possible variance in the random effects to be accounted for. This is as much as there is in the data. This is like our new baseline model 0 going forward. I have labeled these for you so that you can see what each one represents. Here are my fixed effects. These are left over from this previous example. Change slows down in the second period relative to the first. And the correlation between the predicted response time based just on slope 1 and slope 2 with the actual response time, the correlation is about 0.2, which gives me a total R-square of 0.04. So 4% of all of the variance in this response time measure is due to which occasion it is, change over time. We'll see how much more we can get by adding in H. All right. So that's total R-square. Each time we do a total R-square, we'll do the same thing. I'll just change the name of the data set. And you can either do it yourself with proc core, or I have a macro for that for total R-square as well that will print out the R-square cross model so you can look at changes in R-square as well. All right. Okay, questions on any of that? So 1 minute review, what are we talking about? Time invariant predictors are at what level? 2. Are they between things or within things? Between. Can they have random effects? No. What kind of variance do they predict? Between. They're between things. So we're trying to capture random effect variances with between person predictors. That's what we're going to do, okay? Deal? All right, well, what we're going to do now is have office hours, and y'all can get going. So I will be here. Let me know if you have questions, and I'll see you next week.